At each step of scientific computation, it is important and necessary that we have a knowledge of how much of error has been incurred in that particular computation. So, we try to measure this error at each step of computation in terms of the following measures. One such measure is what is called the absolute error. Namely, if x is the true value and we approximate this by x star, say an approximation that comes out as a result of implementing some numerical algorithm, then at that step we have incurred an error whose absolute value is x minus x star. And by a relative error, we mean the absolute value of x minus x star relative to the true value x, and that is what is the relative error that has been incurred in approximating x by x star. Suppose, say, x is a positive real number and I represent x by n digit decimal representation. By that I mean that x is 0 point, there are n digits after the decimal. So, this is a number which I want to approximate to m digit decimal number. Namely, I would like to round off x to m digit decimal representation. Then what do I do? With m less than n, I want to approximate this n digit decimal representation to an m digit decimal representation with m less than n. So, given this x, I would look at x and see what is the m plus 1th digit in that representation, which is given in the form of n digit representation. So, my rounding off of that number depends on what the value of m plus 1th digit is. If the m plus 1th digit is a 0, 1, 2, 3 or 4, then I round off the number which is given as n digit representation such that the first m digits are the same as that of these x, and I discard all the digits beyond the m plus 1, namely m plus 1th digit and the digits after that are all discarded. So, you discard all the digits beyond the mth digit. On the other hand, if the number is a 5, 6, 7, 8 or 9, then I add 1 unit to the m digit and discard all the digits beyond the m digits. The resulting number that I get, I denote it as x star. So, let us take an example and illustrate. If suppose the number is 2722431, so I am given a 7 digit decimal representation of the number, and I want a 4 digit representation of the number, namely I would like to round off this number x to 4 digits. Then what do? I look at the digits up to 4 digits and look at what the 5th digit is. It is a 4, and therefore, I round off this number as x star by writing down the first 4 digits as they are and discard the remaining digits in the representation of x. So, this x star is the rounding of x to 4 digit decimal representation. Say, on the other hand, if x is given by say 0.2722831, if the number is this, again I have a 7 digit decimal representation of a number x, then I require a 4 digit rounding of this number. So, what do? I again look at the first 4 digits and see what the 5th digit is, and the 5th digit is 8, and therefore, the rule is I add 1 unit to the 4th digit, so that I get 2723, and then discard rest of the digits from x. So, this x star is obtained after rounding x to 4 decimal digit representation. If I do this, then this absolute error x minus x star is clearly less than or equal to half of 10 to the power of minus 4. So, in general, if you write down if you obtain your approximation correct to n decimal places by rounding the true value x, then your absolute error will be less than or equal to half 10 to the power of minus m. Let us now see another way of approximation of a positive real number, namely it is called the chopped or truncated approximation. So, in this, given a number x, right, and has a n digit decimal representation, and I want to obtain a m digit chopped or truncated approximation of this number, then suppose I denote it by x hat. It is obtained by simply discarding all the digits in x beyond the mth digit. You do not worry about what the value at the m plus 1th location. You truncate or chop the digits in x and discard all the digits beyond the m digits in the n digit decimal representation of x. So, if I consider say x is equal to 0.4579862, this is x, and what is x hap if I require a 4 digit decimal representation? I do not worry about what digits appear beyond the 4th digit. I simply chop them off, discard them, and then write down the approximation as x hap is equal to 0.4579. If x were 0.237126 and I require a 4 digit approximation, it is 0.2371. I do not worry about what happens beyond the 4 digits. Now, you may ask me, why do we have 2 different measures of error? That is a natural question. Isn't it not enough if we have a single measure of error and we make use of this definition of error and then see how we can control this error after computing error at each step of our computation. I mean, when we look at the absolute error, this is a natural measure of accuracy of approximation. Namely, you have a true value, you have an approximate value, the absolute value of the difference gives you the error that has been incurred. That is a natural measure of accuracy of approximation. But we will show by means of an example that the absolute error is highly misleading. You cannot judge about the accuracy of your computation based on the absolute error. So, it is always better to use the relative error rather than the absolute error. So, let us take x to be 10 to the power of minus 16, whose value is 1125351747 into 10 to the minus 6. It is a very, very small number. So, let me approximate this by 0, be an approximation to x. So, the absolute error in this case x minus x star is going to be this minus 0, which is less than 1.2 into 10 to the minus 7. So, that is the absolute error. On the other hand, if I compute x minus x star by x, then it is nothing but 1. So, this is the relative error. What does it tell? So, this tells us that not many digits are matched in the approximation of x by x star, because the relative error is 1. You have made 100% error. So, your x star and x, they are not matched. Namely, many of the digits in x and x star are not matched with each other. That is what the relative error tells. Whereas, when you look at the absolute error, this tells that the difference is very, very small. So, it looks as though many of the digits are matched, whereas that is not true, is what is given by the information from relative error. So, you may say that this is because you have taken a very, very small number. Let us see what happens if I take a large number and then find out the approximation. So, now I shall consider a very large number, say z, which is e to the power of 16. So, let us write down e power 16, 0.8886110521 into 10 to the power of 7. It is clear that z is very large. So, let us take z star to be an approximation, 0.8886110517 into 10 to the power of 7. So, when I look at this and compute z minus z star, it is 4 into 10 to the minus 3, but this is not very small, even though z star matches with z to 9 decimal places. Although this happens, the difference is 4 into 10 to the power of minus 3. On the other hand, if I compute the relative error, which is z minus z star by z, it is 4 into 10 to the minus 3 by z, which is e power 16, 888,611,0521 into 10 to the power of 7. This turns out to be 0.4501 into 10 to the power of minus 9. What does this show? This shows that about 9 digits in z and z star are correct. So, as I said earlier, you are able to show that in this case z is very large, and looking at z star you will immediately think that your absolute error is going to be a very, very small quantity. That does not happen. It is not small, even though z and z star match up to 9 digits. On the other hand, if you compute the relative error, it clearly shows that the 9 digits are correct in approximation of z star, right, taking the true value as z. So, the absolute error, although is a natural measure, is misleading, and therefore, it is preferable to use the relative error in measuring the amount of error that we incur at each step. Of course, it is clear practically it is not possible, because we have no knowledge of what the true value in any problem. That is what we are trying to solve, and we would like to get approximations. So, in practice it is difficult. However, we will see how we can make use of the relative error as well as absolute error in giving some information about what the error is at each step of our computation, and give also methods for controlling this error. We will now move on to polynomial interpolation. So, we have studied calculus in earlier semesters, and we have understood that calculus provides us tools with the help of which we are able to understand the behavior of functions. But it is necessary that these functions are either continuous or differentiable. But there are several real life situations and applications where the relationship between two quantities are given in the form of discrete data, and therefore, we will not be able to use directly the tools provided by calculus, and this requires that we seek a continuous function which can be obtained from the given data. So, a polynomial is very easy to work with. So, when the information about a function is given at a set of discrete points, we try to seek a polynomial of suitable degree depending upon the available information, such that this polynomial interpolates the function at a set of discrete points. By this I mean that this polynomial passes through the points say x0, x1, etc., xn, at which the information about the function is given in terms of function values. Or in other words, if we want to mathematically formulate this problem, we are given information about the independent variable at a set of discrete points, say x0 to xn, and we are also given the values of some function which may have been obtained by some experimental observations or some measurements, say in the form y0, y1, etc., yn. So, I would like to get or reconstruct this function f of x as a continuous function. So, as I said earlier, I want to seek a polynomial of degree n, say I denote it by Pn of x, such that if I draw a smooth curve in the xy plane of this polynomial Pn of x, it should pass through the points x0, x1, x2, etc., say xn, such that it should take the values y0, y1, y2 at the points x0, x1, etc. So, I want the graph of Pn of x in the xy plane to pass through these points, or in other words, I require Pn of xi to be yi for I is equal to 0, 1, 2, 3 up to n. In this case, we say that the polynomial interpolates the function f of x at the points xi for I is equal to 0 to n. We call these points x0 to xn as interpolation points, and the polynomial is called the interpolation polynomial. Interpolation polynomial. So, mathematically we want to obtain a polynomial of degree n that fits a given set of n plus 1 data points.